this case we have a three-dimensional column that has a fixed connection at both ends.
Is it visible?
No, ma'am.
Now? The screen is visible now?
No,
No,
ma'am.
ma'am.
Okay, let me share once again. Please mute yourself. Someone has unmuted him. Write your roll numbers in the chat box till then. Facing some issues with the this sharing part. So till then, write your roll numbers. Now I guess screen is visible. Screen is
No,
visible.
ma'am.
Just wait for a minute.
It's now it's visible, ma'am.
Okay. Shall we start?
Yes, ma'am.
Okay. So this is another problem. Okay. Same length, cross-sectional area is also same. E is same. All the datas are same. Just the condition is different. Okay.
So very similar to the last video, if you watched it, we had basically this exact same problem, only it was pinned with ball and socket joints at each end. This time we're talking about fixed ends, and that's going to change our effective length that we're dealing with. Now if you remember from a couple videos ago, we had been talking about this
So
stuff.
see, these are the conditions. Okay, different condition. Pin, the wings both hinged, fix free, one will be fixed, another will be free. Fix pin, one will be fixed, another will be hinged, and this is both end will be fixed. Okay, so when the both end will be hinged, your effective length will be what? LE will be L. When one fixed and free condition, your LE will be 2i's of L. When you have this combination, so these values should remember. Okay.
Are different situations where we have like pin, fixed end, and free end, a fixed end with a pin end, and a fixed end with a fixed end. Well, this is the situation that we have here in this video. So we're saying that that means that our effective length is going to be equal to 0.5 times the actual length. And so in this case, our actual length is 3 meters.
Ma'am.
So our effective
Yeah.
length, let's not draw an equal sign, let's draw
Yes.
an arrow.
Yes.
So we have our
The
effective length is going to be
condition, ma'am.
equal to
What is
0.5 L,
What
so
is?
that's 1.5 meters. Alright, and that is coming directly from that last, not that.
Okay. earlier both in earlier problem we solved for both and hinged. Okay, when the both hand will be hinged, your effective length will be equal to L. So that in that problem your length was same, right? Your length was, let me note, there in earlier problem your L, we have taken the 3 meter only, right? Because both hand were pin. Now in this case your both end are fixed. Okay, so in both ends what happened? Your effective length becomes L by 2. That's why what is L? My L is 3 meter. So divide by 2, it will be 1.5 meter. Okay. Now your effective length, since this is the condition, both hand are fixed, it will be written in the question that both hand are fixed or hinge, what the conditions will be given. As this is the both hand fixed, your effective length will be 0.5 of L. Okay. So that's why we have found out L is equal to 3 meter by 2, 3 by 2, and it is 1.5 meter. Okay, hope it is clear. So let's continue.
Last video, but a couple videos ago where we talked about that. Okay, so when we start talking about this for buckling, is this column as a rectangular column, it can buckle in two different directions or planes, basically. It can buckle in the YZ plane, basically going out that way or coming this way, and it can buckle in the XZ plane, so basically kind of going into the page like that or out of the page like this. So we need to check what the critical load is for each possible direction it can buckle in, and then from there we can use the factor of safety to determine the allowable load, and then after we'll also check to make sure that this thing, to see if it's yielding before it's buckling or whatever. Alright, so the formula that we need to use, just like the last couple of videos, was P is equal to P crit is equal to pi squared EI over L E squared, right? The effective length squared. So in this case, we do need to identify the moment of inertia that we're going to be using in each direction. So for buckling in the YZ plane, just like the last video, we need to find the moment of inertia about the y-axis. And then for buckling in the XZ plane, so this way, we need to find the moment of inertia about the x-axis. And we did calculate those in the last video, so I'll just write them right here. And then we want to use each of these when we calculate for buckling in each of the planes. So let's take a look at buckling in the YZ plane first. So we want to figure out what the P critical is in order for that buckling to happen. So then we're going to have to use the subscript here for I, Y, moment of inertia about the y-axis when we're dealing with buckling going like that. Alright, so when we have all of these values, we have the effective length, we have the moment of inertia, we have E, we have pi, obviously. So we're going to find that the P critical in the YZ direction is 23.4 kilonewtons. And now we want to repeat the process to find the critical load for buckling in the XZ axis. So let's throw in some subscripts here. XZ, and this time we need to be using the moment of inertia about the x-axis, so we have subscript x up here. Alright, so when we go and plug in all of those numbers, we're going to find that the critical load for buckling in the XZ axis is 93.6 kilonewtons. So now what we do is we select the smaller load as our actual critical load, because obviously if you surpass the smaller load to get up to the bigger load, you already would have buckled in that direction or in that plane. So what we do is we take this, and if we're asked to find the allowable load for buckling with some safety factor, we can do that. We just take our factor of safety, which is equal to the ultimate load to the allowable load. So we can just rearrange that so we get our allowable load is going to be equal to 23.4 kilonewtons over a factor of safety, which is 2.5. Alright, and that works out to be 9.36 kilonewtons. So with a factor of safety of 2.5, then we can safely support this compressive load here of 9.36 kilonewtons. Now, something that we should do is just like exactly like we talked about in the last video, is we should check that.
So in the same problem, In the same problem, we have found out first I, y and moment of inertia along the y-axis, moment of inertia along the x-axis. Okay, then we have found out the critical load about the both axes, and to find out the allowable load. The allowable load means at what the load we can allow on this column, over this column. Okay, so we have to take the lesser value, so we have taken the lesser value divided by the factor of safety given to us. Now we got that our allowable load is 9.36 kilonewton. Okay,
We're not at risk of yielding with this applied load. So let's just give ourselves a little bit more space down here. We know that the yield stress for this material in this problem is 250 megapascals, and we also know that stress is equal to force divided by area, so we have P over A, and in this case for yield stress, that is our ultimate strength, or our ultimate load here, so we can say Py or P ultimate, whatever. It's a load that's going to make the material yield. So what we do is we just have to rearrange this to solve for Py. So we know that the area up here, the cross-sectional area, is 800 millimeters squared, so we get 250 times 10 to the 6 newtons per meter squared, that's megapascals, times our area, which is just 800 times 10 to the negative 6 meters squared, and that's going to be equal to 200,000 newtons, which is 200 kilonewtons, and basically this material, when we look at this, this material will yield when we apply 200 kilonewtons to this exact column, and that's way more than if we applied only 23.4 and it's going to buckle. So it's safe to say that this column will buckle in the YZ direction or plane before it even buckles in the XZ plane and before it yields due to compression.
so hope you understood this problem. Okay, now let's see the another problem. Let's solve another problem.
Three for column in this video, we are looking at example number 3.
Screen is visible. Now in this case, one end is fixed and one end is free. Okay, we'll solve for one end fixed and one end free. Screen is visible. Okay.
3 for column buckling. In this case, we have a column with one fixed end and one free end. In this case, our column is not rectangular like the last two examples. We're dealing with a W shape, which basically stands for wide flange shape. And the name of this wide flange shape is W360 by 44. You can look this up in the back of your Mechanics of Materials textbook, and basically any textbook will have tables for this sort of thing, and from there we can figure out, it just basically prints, it has all this information, it has all the moments of inertias in both directions, the cross-sectional area, the depth, the thickness, what else does it have? radiuses of gyration. Basically everything you need to know about these columns is in the table, and so that's where these numbers come from for this y-infinite shape. Alright, so when we're looking at this, this is we have one fixed end and one free end. So if you remember from a couple videos ago, we had these diagrams. Well, in the case where we have a fixed end and a free end, this is this guy, the effective length that we're going to be using in this expression for P critical is twice the actual length of the column. And we have to make sure that that's in both directions that this can possibly buckle in. So this column can buckle in the YZ plane, basically going out that way or coming this way. And it can also buckle in the XZ plane, so basically going kind of into the page that way or out of the page this way. No matter which way we look at it, both of those are considered to be fixed and free. So we are going to use the effective length of 2L for both of our calculations. So let's maybe put this here. So we have LE is going to be equal to 2L. So the effective length that we're dealing with is 6 meters. Alright, so let's go and grab this expression up here. Alright, and let's start our calculations. We can calculate for buckling in the YZ plane first. So what we want to do is just drop this in here. Let's put in some subscripts. So we have, for calculating for the P critical that would cause buckling in the YZ plane, let's give it that YZ. And in that case, we're looking at the moment of inertia about the y-axis here. So we need to give it that subscript, right? Because if we're looking at buckling this way, basically if this is the top-down view, it's going to be going out that way. So we're looking for that moment of inertia about the y-axis. Alright, so if we just plug in all those values for buckling in the YZ plane, we're going to find that it's 449 kilonewtons. And then we want to repeat this calculation for buckling in the XZ plane. So we'll just change our subscripts here. So we're looking for buckling for the P critical in the XZ plane. So that means we're going to be looking at using the moment of inertia about the x-axis here, so we'll give it that subscript. So if we go and plug all of that in, we're going to find that our P critical for buckling in the XZ plane is 6,639 kilonewtons. So the actual P critical for buckling in this case is going to be 449 kilonewtons, because obviously if we go all the way up to 6,000 to reach buckling in the X.
Why you guys are making noise? Someone please tell him to mute himself.
Z plane, we already will have buckled in the weaker plane, which is the YZ plane. Now, if we do want to maybe figure out what our allowable load is, if you're given a factor of safety, then all we have to do is we just say that our factor of safety is equal to our ultimate load over our allowable load. So in this case, all we have to do is switch those, and we're getting our allowable is going to be equal to our ultimate, which is in this case our P critical, so 449 kilonewtons, and we would just divide that by the factor of safety, so divide by 2.5, and that's going to give us an allowable load of 179.6 kilonewtons. So that is our that's our allowable load, P allowable. This was P crit, and there we go. Let's throw a box around that guy too. Oops, not a straight line. We want a box. Boom, like that. Alright, so we found our actual P critical. We found our P allowable. One other thing that we should do is we should just check that this column is not going to not going to yield before it buckles. So all we have to do is pretty fast check there, so we just know that we have our yield stress. There we go. So our yield stress is equal to 250 megapascals, but the stress is also equal to force over area, and this is the force that is going to cause us to get yielding. So we that's what we're looking for here. So we have P is going to be equal to 250 megapascals, which is 250 times 10 to the 6 newtons per meter squared, times our area. Again, this area for this W360 by 44 wide flange shape comes from the tables in the back of your Mechanics of Materials textbook. So that is 5730 times 10 to the minus 6 meters squared, just that unit conversion right there. And that is going to give us 1,432 kilonewtons. Alright, so that is the actual force that's going to cause us to get yielding. Note that 1,432 is a lot bigger than 449, so we are going to be getting buckling before we get yielding. But if you're also curious just what the allowable, if for some reason if you want to know what the allowable force is for yielding, same thing, we would just divide this by our safety factor of 2.5, and that would give us a P allowable for yielding for 572.8, right? That's just that divided by 2.5. But clearly, the allowable force so we're safe from buckling is 179.6. So this one is going to govern, and we won't be able to apply anything more than that if we want to keep within our factor of safety of 2.5 and be safe from buckling.
So that was all about, so we have discussed your 3 problems today, okay? So try to solve. Okay, let's see one more problem. Okay, then it will be easy for you. Solve all the 4 problems, and if you have any doubt after that, let me know, okay? Those who have joined newly, they can write their roll numbers.
Number 4
The
of
screen is
column.
visible?
Yes, ma'am.
Okay. So this is a problem, one end fixed and one end pinned. Okay, one end fixed and one end pinned, and the values are the same. So see how to solve this one.
Buckling. So in this example, we have a rectangular column that's fixed at one end and it's pinned at the other end, but this pin only works in one direction. Basically, it's for buckling in the YZ plane, the column sees this connection as a pin, but for buckling in the XZ plane, there's really nothing stopping it from swinging out if it was to buckle, so the column sees this as just being free to buckle in the XZ plane. So when we look at, if we go back to a couple videos ago, as always, we had these situations up here. So in the case of a fixed, let's do a fixed connection at the bottom and a pin at the other end, then the effective length that we're going to be using in our P critical formula is 0.7 times the actual length of that column. And then for a column that's fixed on one end and free at the other end, we're using effective length of 2 times the actual length. So depending on which way we're considering buckling to go in, we're going to have to use each of those. So maybe let's write those out. We'll just say that we have our effective length for the YZ plane. This is going to be where we have a fixed pin connection, so that will be equal to 0.7 L, and 0.7 times 3 there is just 2.1 meters. Alright, now our effective length that we're going to be using in the XZ plane is was 2L for the fixed and free connection, and so just 2 times, so we can write that 2L, so that's just going to be equal to 6 meters. Alright, let's go and grab this expression up here. We are going to need the moments of inertia about the x-axis and the y-axis, and we've already calculated those in previous videos for this exact cross-section, so I won't bore you with those. And we're just going to plug them into the p-critical expression. So let's just give us, we have to do this for each possible direction for buckling. So let's check the YZ plane first, and that's going to give us the subscript IY, because it'll be buckling in this way or that way. So basically, from the top-down view, it's about the y-axis there is the moment of inertia that we're concerned about. So when we plug all that in, we just get it to be equal to 12 kilonewtons. And now we just want to check for buckling in the XZ plane. So let's just bring this down here, and we'll add in our subscripts. So we're looking for P critical in the XZ plane, which means we're dealing with the moment of inertia about the x-axis. And then again, this is the effective length for the XZ plane. Alright, so when we just plug in all the values that we already have, we find that to be 5.9 kilonewtons. And 5.9 is smaller than 12, so when we look at this, the actual P critical that we're going to get for this column is 5.9 kilonewtons. We're going to be getting buckling in the XZ plane before we get buckling in the YZ plane. The other thing that we can do here is we can just check the allowable load if we want, based on the factor of safety. So let's just write it down here. We have factor of safety is equal to the ultimate load over the allowable load. So if we just rearrange for the allowable load, we will just get the ultimate load, which is 5.9 kilonewtons, divided by our factor of safety, which was 2.5. And that's going to give us an allowable load for this column of 2.95 kilonewtons. This is equal to P allowable. Alright, so let's throw a box around that one as well. That's our allowable load. And the last thing that we want to do here is we just want to check to make sure that the column doesn't yield before it buckles. We've been doing this in the previous video, so all we do is we know that our yield stress is equal to basically just the force over area, and that force is the force that would cause this material to yield. So if we just rearrange for P, we're going to get our yield stress, which is 250, so we have 250 times 10 to the 6 newtons per meter squared times 800, well this actually, I should write it up here, the area is equal to 20 times 40, so that's 800 millimeters squared. So in units of meter squared, that's just 800 times 10 to the minus 6 meters squared. So if you just multiply those two together, we're going to find that the force is 200,000 newtons, or in kilonewtons, that's just 200 kilonewtons. So 200 kilonewtons is way bigger than 5.9 kilonewtons, and it makes sense. This is an extremely slender column. When we're looking at this, it's only 2 centimeters by 4 centimeters in its cross-sectional area, or cross-sectional dimensions, and it's 3 meters long. So no wonder this thing is going to buckle way sooner than it yields.
So today we see we have solved all the 4 problems with all the 4 conditions. So revise it by yourself. Okay, go through the video and practice it by yourself, taking the same values, or you can take some another values also. I'll share some practice sheets also. Okay, soon I'll share some practice sheet so that you can be more familiar with this. So those who don't leave the class, okay. So those who have joined newly, they can write their roll numbers. Okay. Okay then. See you in the next class. Thank you.